Recording on. All right, so this is lecture 8. Today is the 16th of uh, April. So let's see what we have been discussing, and we want to continue that discussion. And so let me quickly summarize. We've been talked about energy methods, okay, and the general approach or general formulation, which was Rayleigh's method. Okay, let me see. All right. So Rayleigh's method, we discussed that. Okay. So to summarize, um, what was Rayleigh's method? Rayleigh's method, which is based on the concept of conservation of energy, right? Um, Said what? If you have any simple structure, let's say a beam, a cantilever beam with bunch of lumped masses and bunch of um, lumped springs, if you may have a simply supported beam with bunch of masses and a couple of spring supports, okay, that's a rotating machinery. The way, I mean, that formulation was done was based on the assumption that if this structure is vibrating and the amplitude of the vibration is small, is a low, small vibration, the shape of the static deflected shape of the structure is analogous to the dynamic displacement shape. And based on that assumption, what did Rayleigh said? You consider that single degree of freedom, let's say the maximum displacement at the tip or the maximum displacement in the center, which is what you're interested in, okay? And you can write the displacement at any point, although it is now a function of time, related to that the displacement at that location with a single degree of freedom times this shape function. And how do you find the shape function? This is from the strength of material, from um, basically by relating by finding the equation relates the displacement at any point to the point of interest. So it was based on that Rayleigh set up the kinetic and potential energy, and then did this formulation that it resulted in identifying the equivalent mass and equivalent spring, or the combined effect of, in the, let's say, if you look at a case like this, combined effect of all these masses, including the mass of the beam. The equation was you take the integral from 0 to L of mass density times that shape function squared, okay, this integral. Mass density here is density per length. So if you're given the mass per volume, density per volume, multiply that by the cross section, plus the contribution of those lumped masses, which come down to be each of those masses times the square of this shape function evaluated at the location of that mass. So this is how you find the equivalent mass. And for the equivalent stiffness comes down to finding this integration, which is what you've had in the strength of materials, okay? Remember this. This is nothing but that differential equation, right? That you had in strength of material, or plus the contribution of each lumped spring, which is the stiffness of each times the square of that shape function evaluated at the location of these springs. So in order to find the natural frequency of any structure, you don't have to use the energy method from scratch. All you do, just formulate the mass and the equivalent spring by using these Rayleigh's expressions, okay? So let me just show you a simple problem first, and then I'm going to discuss the project that you will be doing. So let's demonstrate, for instance, uh, very quickly how you can apply this approach to a problem like this. Let's say you have a cantilever beam, okay, that in its middle is supported by a spring. These quantities are given. So mass is given as 10 kilogram. Length of this beam is given as 10 meters. The stiffness is 100 Newton per meter. Modulus of elasticity is given as 200 gigapascal, and the cross section is given is 10 centimeter by 1 centimeter. So I would be 1/12 of B H cubed. So 10 times 1 cube. Okay. Centimeter to the fourth. Okay. Okay. And the mass density is given as 7,860 kilogram per meter cube, which is for the steel. So you need to convert this to uh, kilogram per length. So you need to multiply this by the cross-sectional area. So this is 10 times 1 times the negative 10 to the negative 4, because this is in centimeter, so convert it to meters, okay? So multiply this, that becomes kilogram per meter. And that's what you use in these equations. So we already,
Professor, can
yes,
you move your paper up just a little bit?
sure. Sorry, that's kind of tiny. I did not do a good job here, messed it up. So rho comes out to be 7,860 times 10 times 10 to the negative 4, or 10 to the negative 3 then. 10 to the negative 3. That's kilogram per meter. So how do you solve the problem? The first step is to identify that shape function, okay, which is what we had done in previously last time. We know for a cantilever beam, this is that displacement function, 1/2 of x over L cubed. So K equivalent is what? Is the integral from 0 to L here, E I, second derivative of this function, okay, square that, dx, perform this integration. Plus, you have a lumped spring in the middle, so you need to evaluate that contribution of that by multiplying that stiffness times this function that is evaluated at the location of this spring, which is L over 2. So all I need, just substitute these values. So E and I are constant, so come out of the integral. You have 0 to L. Um, So if you take the second derivative of this, you see that it would be 3 over L squared minus 3 over L cubed times X. square that, okay? And evaluate this at this function at L over 2, you see you will get something like this, 3 1/2 times. Since this is L over 2, L and L cancel out. So you just have 1/2 squared minus 1/2 of, again, L over 2. So L and L cancel out. 1 over 2 cube and square root that. If you simplify all of these, okay, you, by substituting K and so on, you, K is given as 100 Newton per meter. You'll see that this, first of all, this is 3/2, this is 1/2, so it's just simply 1. Okay, so you see this comes out to be EI plus K. So I'll just write that as this. That's it.
Professor,
Yes.
could you kind of repeat that? You said that 3/2 and 1/2 cancel.
Show you. Let me show you actually right here. See, what I'm doing is this. Let me not skip it. So you're evaluating phi squared at x equal to L over 2. So phi is 3/2 x over L squared minus 1/2 x over L squared. So you substitute for x to be L over 2, right?
Yeah.
So this
Professor, isn't it x over L cubed on the end? 1/2 x over L cubed?
x over L cubed, yes. Oh, here you mean? That is x over L cubed.
You wrote it down as x over x squared, x over L squared on your second paper.
Oh, here.
Yeah.
Oh, sorry about that. Yes. Okay. Yes. Yes, it is cubed. So this would be 3/2. If you substitute x L over 2 would be just 1/2 squared minus 1/2. Substitute for x, which is L over 2, you have 1/2 cube. Okay.
Mhm.
So if you evaluate these, you will see that comes up to be 1. Okay.
Oh, okay.
So with
Thank
that, oh, you're welcome. So that's K equivalent. You do the same thing for mass equivalent using this equation. Okay. So I will write that down. You have mass equivalent. You have only one lumped mass here, and this. So you have integral from 0 to L of rho phi of x squared dx plus that lumped mass times phi squared evaluated at the location of that mass, which is L. Rho is constant, you take that out, integral from 0 to L of 3/2 x over L squared minus 1/2 x over L cubed, square of that, dx plus m. If you evaluate this, you see this is going to become 3/2 minus 1/2. So that's just m, which is that lump mass given at the tip. So if you simplify this, you get rho times, this is just this is like a minus b squared. So just a binomial. So it would be a squared plus b squared minus 2ab. So I expanded that. It becomes 9 over 4L4 integral from 0 to L of x4 dx So there are three terms here, right? So it reduces down to three integrals plus 1 over 4L to the 6 integral from 0 to L of x 6 dx, then minus 2ab, 3 over 2L5 integral from 0 to L of x5 dx plus that m. Okay, if you simplify this, you get 0.2357 rho times L plus m. So that's going to be m equivalent. So you had K equivalent was EI plus K. Just substitute these values. I have to admit, I didn't complete this, finish this example, but you can just substitute these numbers and then simply find the natural frequency. Okay, I just gave you, this example as a sort of a introduction to give you the project, which of course the project is fully described in the exam that I will give you, but I want to go over that because it's the first project you're doing in this class. And unfortunately, the only project, because during non-COVID time, I also gave a very comprehensive project that you had to build something and test it, find the natural frequency experimentally by analytically and using Rayleigh's method. It was fun. And some students did some really fascinating, built some fascinating devices. I have them in my office that versus measured the rotating unbalance or transmissibility and so on. It was really fun. Hopefully when the school goes back again to normalcy, we can resume those fun projects. But anyway, I'll give you just one for this class. And what is that project that I'm going to give you? This is the project that I'm going to give you. So let me explain what it is. Okay, this is project one. I want you to consider a simple structure versus a cantilever beam. A cantilever beam can be what? You take a straight edge, a ruler, steel ruler, and you clamp it to somewhere, okay? And let's say, this is one example. Let's say you have a ruler. It is 27 and 1/8 of an inch, which is 18.75 inches. The cross section is 1/4 in depth and 1 inch in width. This is made of steel, so the density is 0.283 pound of force to inch cube. That's one of the things I don't like about English units. So you need to convert this to about pound mass. E is 30 times 10 to the 6 PSI, and I is 112. From here, this is B, this is H, would be 0.25 cube inch to the 4th, okay? So this is what I want you to do. Consider a beam like this, or you can consider some, some simple case, like a cantilever beam. Put that ruler and bolt it here, not clamp, because you want to have rotational allowed. And then do this. Use the exact formula, which I will give you, and I will discuss it right now. Find the natural frequency. Then use Rayleigh's method. Find the natural frequency. And then experimentally measure the natural frequency of this structure. How do you do that? Let's say you have a ruler, right? I don't have one to show you here. Okay, let me see. For the lack of a better example, maybe I can use something here. Okay, let's assume this is that a ruler. Okay, so you've clamped it here. Okay, you've clamped it here, and then you just disturb it. Of course, this is too stiff. Starts vibrating. Of course, this is too stiff, so it stops quickly. But anyway, you vibrate it, and you can use the video recorder on your phone or whatever and measure the cycles per second. So theoretically speaking, this is an undamped system. So when you vibrate that, this is going to be the response, right? So if you measure the cycles per second, convert that to radians per second or hertz, you can find the natural frequency peak to peak, okay? Peak to peak measurement in one cycle. Let's say you measure how many times, let's say in 1 second, okay? You count the cycles, how many times per second it reaches the peak displacement as you are disturbing it, okay? It goes like this, right? Peak to peak. How many times in a second? That's cycles per second. But anyway, you can do that quickly. And then I want you to compare these. So let me show you what, for instance, if this is your ruler, what you would be expected to do, okay? So I'm going to solve that problem, actually, solve that particular problem. So let me do that, okay? Okay, there is, okay, so let me redo this. You have this beam. Let's say this is what you have considered, clamp that, okay? This is your beam, okay? 27.1875, 1 inch, quarter of an inch, 1 inch. Okay. There is a book called Formulas for Natural Frequencies and Mode Shapes. I forgot the name of the author. I guess it was Blevins. Maybe I'm wrong. But anyway, Formulas for the Natural Frequencies and Mode Shape. This was actually a PhD dissertation of that fellow done, I don't know, in the 60s, that he considered a large number of simple structures from a cantilever beam and simply supported, some simple frames, clamped beam, and so on. And using the continuous mechanical vibration of continuous systems, which takes you to all kinds of interesting partial differential equation. That's actually a course in itself. Evaluated the exact natural frequency and mode shapes of all those simple structures and tabulated those. They're available. Now they're online. You can Google it, find the natural frequency for a cantilever beam or a simply supported beam. If you do that, you'll see that for a cantilever beam, which this is, the exact formula for the natural frequency is given as 3.516 divided by L squared square root of EI over M sub bar, where M sub bar is the mass density per length. Here we are, as I said that, you are given the mass density per volume converted. So let's demonstrate that for this beam. If you use this formula, you have 3.516. Length was given as 27.1875 inches squared. So all units should be in inch. E was 30 times 10 to the 6 pound per square inch. I was 1 over 12, 0.25 inch to the 4th. So this is PSI, this is inch to the 4, divided by this. This was given as 0.283. Multiply that by the cross-sectional area, which is 1/4. This is pound force. So you need to divide that by 386, okay, which is the gravitational acceleration, 32.2 times 12. So to convert that to pound mass. So if you do that, so this is 12 times 32.2. I don't like these English units. If you do that, the end results would be 69.442 radians per second. Omega exact. Or in hertz would be 11.052 hertz. Let's use Rayleigh's method for a simple beam like this. See how much natural frequency would be using that. So you have just a cantilever beam, no lumped masses, no lumped springs, just a simple beam. So mass equivalent would be simply the integral from 0 to L rho phi squared x dx. So this would be, rho is constant, take it out. So it would be 0.283 times area, mass density per area, divided by 386. I factored that out because you want that to convert that to pound mass. Integral from 0 to L. This is squared, which is 3/2 x over L squared minus 1/2 x over L cubed. Okay, square of that dx. If you evaluate this, you see this comes out to be 12.326 pound mass. That's the mass equivalent. Do the same thing for this stiffness. For the stiffness, of course, you have just a cantilever beam. Of course, you can use this integration, okay? But the end results would be just 3EI over L cubed, stiffness of the cantilever beam, okay? So this would be 3 times 10 to the 6, okay? Again, times I, which is 1/12 of times 0.25 cubed, divided by L, which is 27.81875 cubed. This comes out to be 583.141, okay, pound per inch, okay? So this is K equivalent. This is mass equivalent. So from Rayleigh's method, you find this if you take the square root of that 583.141 divided by 12.326. This comes out to be 68.78 radians per second. Okay. Or in terms of hertz, comes out to be 10.947. Compare this with what we got from exact value. Okay. If you, let's see what the error would be. Error would be 11.052 minus 10.947 divided by 11.052 times 100. You get this to be roughly about 0.95%. So you can see the beauty of Rayleigh's method, that how closely it estimates the natural frequency of this structure. For your project, I can guarantee you, if you do things right, you should get an error less than roughly about 4%, based on the experience I've seen the students doing in this project. If you get a more than 5%, you're not doing something right. You're maybe the clamped end is not good, or I don't know. You have to go and check your calculations. But that's all I want you to do. Any questions? Okay. So that is the project. Again, I have fully described it in the statement of the problem that I will give you. So any questions? No question here. If not, let's pause here and summarize what we have done, because now we're going to start really what is the heart of mechanical vibration. Okay, so let's see. I told you as far as the classification, are you sure you have no question? Classification of the topics. In general, mechanical vibration is the study of vibratory motion of systems when they are freely vibrating, so we call that free vibration, or when they're vibrating due to the action of a force that is, continues to stay on the system. And so this is called transient vibration. This is steady state or non-transient. There are different terminologies used, but anyway, these are the two classes of vibration that we are going to study. But for each case, we do consider the system to be either undamped or damped. So undamped and damped. So far, what we have done, we have basically studied this category. We introduced that. In fact, that helped us to develop the model for the system, and also to study how we can model relatively complex structures by setting up this model, which is a single degree of freedom undamped system. We introduced the concept of natural frequency and set up the equation of motion. and demonstrated that solution or the response of an undamped system is, a sinusoidal function that you can write it either like this or like this, where the frequency of this oscillatory motion is the natural frequency of the system. In fact, that's how we defined natural frequency, because this was the natural motion, natural vibration of an undamped system. So the frequency of that motion, which is sinusoidal motion, called the natural frequency. We showed you how you can actually solve for these constant by using some initial conditions. Let's say at time equal to 0, you have the value of the displacement and the velocity. So we set up also the response in terms of those initial conditions. But that's all we have done so far. And of course, we mainly focus on methodologies to derive this equation of motion or model the system. And that's how we introduced the Newton's law, we use Rayleigh's method, and so on. Now that we have a good grasp of all of that, we are going to move to the next category, which is this: free vibration of damped systems. This is an important topic because we will now introduce another quantity besides the natural frequency, which, as I said, is one of the important or fundamental dynamic characteristics of the system. Now, by studying free vibration of the damped system, we introduce yet another quantity, which you will see is a damping ratio. And also, we study the response of the system, which introduces some interesting observations. So what do we have here? If you could remember the model that we set up for the general vibratory system or any structure looked like this, consisted of these three components. And we used, of course, second law of mechanics to set up the equation of motion, right? This is the mass moving in that direction. So this is the lumbar force. This is the force of the spring. This is the force of the damper. This is Ku. This is Cu dot. And we set up the equation of motion, which looked like this, right? So what is different in this equation, the only term that is being added is this. But this is, in terms of mathematics, the second order linear homogeneous differential equation. How do you solve this problem? Okay, how do you solve? What is the solution to this equation? If you remember from your differential equation, you do assume again the roots are of the form e to the lambda t, substituted in this equation, simplify that, you do end up with this equation, which we call that characteristic function. Roots of this equation, this is quadratic equation, right? Or what? Roots of this equation are going to be 1 over 2m minus c plus and minus square root of c squared minus 4km. So once you have these roots, solution of this equation, which is the response solution of this equation, would be linear summation of these two roots, which are this. a linear summation of the responses that are obtained for these. In other words, the solution is, there are two solutions. One would be A1 e to the lambda 1t, U2 is A2 e to the lambda 2t. I don't want you to remember all of these, but that's the solution to this differential equation. Okay? Now, we want to pause here. Before we go any step further, this is a very important case that I want to discuss. If you look at this equation or these roots, you can make a simple observation, and that is the value or the sign of these roots depends on the value or the sign of what we have here under this radical. We will establish a baseline. What is that baseline? Let's establish the baseline that when the c squared minus 4km is 0, which is one of the possibilities, depending on what the value of the damping, the stiffness, and mass is, we may have a case that this value under the radical is 0. Or in other words, I will rewrite that here, that in other words, c would be 2 square root of km if you find the value of c from this equation. In other words, it is possible that the damping coefficient, okay, is such that it is twice the square root of km. We call this special value as the critical damping coefficient. We'll see the importance of this. But let's, for the time being, just play around with the mathematics of this problem. So we designate that as C sub C. So C sub C is this critical damping coefficient. But let's look at this. I can multiply this by the square root of m divided by the square root of m. You say I'm crazy. Why am I dividing and multiplying this by 1? This is what I would do. I will look at this operation differently. Let's consider separate these two. In other words, rewrite this as 2 square root of k over m times the square root of m times the square root of m. That's what I've done here, right? So this becomes what? 2, what is k over square root of k over m? The natural frequency. What is square root of m times square root of m? M. So if the value of damping in a system is such that it is equal to the critical damping, that value of the critical damping, we demonstrated that is equal to the 2 times mass times the natural frequency of the system. So in the case that solution of this differential equation is such that we have this equal to 0, or the two roots are equal, these two roots would be equal and will be minus that c sub c divided by 2m. C sub c is 2m omega n. So these two roots would be simply negative of omega n. Okay? And we call this case critically damped system.
Can you move your paper up a little bit?
Oh, sure. Sorry about that. Here we go. So when that's the value of the damping, the two roots become equal and it's critical. So, and that obviously from here, if this is 0, you see that the two roots would be minus C over 2n. C in this case is the critical damping. So the two roots are equal to negative of natural frequency. And we call this the case of critically damped system. This is the baseline. As I said, for the lack of a better word, I consider that a baseline. We will start from here and introduce, in fact, or discuss all possibilities that we encountered in a vibratory motion of a system that is damped, which, as you will see, we categorize them to the case of critically damped system and non-critically damped system. So we'll discuss those next time. If you have any questions, please let me know. Otherwise, I'm going to stop and see you during my office hours.
Thank you.